But before the history of Hessian equations started, there was work of Gording, who studied hyperbolic polynomials. Here you see the definition: polynomial p of degree k in Rn is hyperbolic with respect to point vector a if for any b, if you take the line in the direction of a, it has exactly k real roots. And this theory applies in particular to elementary symmetric polynomials of any degree. And they are defined here, and we use this notation for the polynomial of degree m. In particular, the Gording results imply that the positive cone gamma m, defined here, so you require that the symmetric polynomials are positive for all k between 1 and m. So in particular, he proved that this cone is convex, and the function Sm to the power 1 over m is concave when restricted to this cone. There are some classical inequalities quite often used when we deal with Hessian equations. So here we produce this by taking the derivative with respect to lambda I, or if we replace lambda I in the definition of Sk by 0. So we have Newton-Maclaurin. So it's a combination of two inequalities. We take lambda from this positive cone gamma m, and then for different j and I, we have this inequality when I is bigger than j. And the next one, usually called Gording inequality, we take lambda and mu from this positive cone, and well, we have this inequality there. Here we replace this lambda I by 0, and here we have just symmetric polynomials of degree m for mu and lambda. So now we take a Hermitian n by n times n matrix, and we consider the eigenvalues. And by abuse of notation, we again denote by Sm, but this time of the matrix, the symmetric polynomial of eigenvalues of this matrix. Having this, we can define the complex Hessian equation. So we have a given function f in some domain in Cn. By A, here we denote the complex Hessian of the unknown function u. So the complex Hessian means that we differentiate once to holomorphic coordinate and once to with respect to anti-holomorphic coordinate. And then we compare this symmetric polynomial acting on eigenvalues of this matrix to the given function f. So this is the classical form of M Hessian equation, M standing for this degree here. But I will use mostly this form of the equation where we use differential forms. So D is the usual differential operator, DC the operator we usually use in complex analysis. So up to the normalizing constant, this equation is the same as this. So beta is the standard Euclidean form in Cn, and ddcu to the power m is the wedge product m times of this expression. So we shall consider the M Hessian equation in this form. So this equation is elliptic with respect to M subharmonic functions. Function which is C2 smooth is called M subharmonic if the Hessian matrix of this function has eigenvalues in the closure of this positive cone gamma m. So it can be restated in this way that for k between 1 and m, we have inequalities of, so we have on the left-hand side, we have positive form. Much older history have real Hessian equations. They were studied since 80s. The basic paper by Caffarelli, Nierenberg, Sprague. So first they solved the Monge-Ampère equation in this context, but then also generalized this to real Hessian equations. So then you have, of course, a different space of functions. They are so-called M-convex functions, which among which you try to find a solution. And they solved the Dirichlet problem for positive smooth data. Iwoćkina had some important a priori estimates, and Trudinger-Wang, they also considered weak solutions, not necessarily smooth. In this context, trying to do some kind of something similar to pluripotential theory in complex variables. In general, if m is equal 1, then we have just a Poisson equation. For m equal n, so the dimension of the space, we have complex Monge-Ampère equation, which is in many respects different than the general M Hessian equation, because in this case, we have all positive eigenvalues. And in general, it is not the case. So now coming back to complex Hessian equations, the first results were obtained, this is a bit strange story, by Vinakua in '86. He was a student of Nierenberg. So he did it as a PhD thesis, but then he moved to some applied math. So it seems that his papers, well, he published a part of the thesis in the paper, but it seems it was forgotten later, and that's why he reproved more or less the same thing in '06. So what is the statement? So we have a smoothly bounded, relatively compact domain in omega. We suppose that the boundary is what we call m minus y1 pseudo-convex, which means that if we take the Levy form at any point of the boundary, then the eigenvalues are in this cone. Then we impose the Dirichlet data, so the boundary condition phi and the strictly positive function on the right-hand side, also smooth. And then they solve this Dirichlet problem following more or less the method of Caffarelli-Nierenberg-Sprague. It's not much different from the proof for the real case. Later, Błocki started to study weak solutions of M Hessian equations. So far, we have defined M subharmonic functions for C2 smooth functions. If you want to deal with weak solutions, you have to relax this smoothness assumption because, well, all M subharmonic functions are in particular subharmonic. So they are a priori on the upper semi-continuous. So in this definition, first you have to start with the bracket. So alpha is called M positive form. If we have inequalities like this for j between 1 and m. And then, considering all such forms, we take this wedge product. And we require that this is true in the sense of currents or in the sense of distribution theory. And if so, then U is called M subharmonic. So Błocki initiated the study of those weak solutions, in particular their integrability. This is a very interesting problem related to this. So if you look at this function, this is kind of fundamental solution for M Hessian equation. Yeah? Yeah. If it is, yeah, of course. If it is C2, then yeah, sure. So we look at LQ locally for Q smaller than this. And well, his conjecture, still open in general, says that any M subharmonic functions belongs to this space. And here, this function gives you proof that it cannot be any better, because this belongs exactly to LQ if Q is satisfies this inequality. And this is kind of green function for M Hessian equation, because it puts, it is if you apply the M Hessian operator, is 0 away from 0. But with Sławek Dinew, we were able to confirm this conjecture under extra assumption that the function is bounded near the boundary. As I said, the general problem is still open. But this weaker result was enough to obtain certain volume capacity estimate, which enabled us to find the existence of weak solutions to the Dirichlet problem when the right-hand side is in LQ for Q satisfying this inequality. Then you, again, you consider smoothly bounded M-1 pseudo-convex domain. You put a continuous data, and we found continuous solutions up to the boundary of the M Hessian equation. This bound on the exponent, this n over m, is sharp because of this, again, because of this green type function from the previous slide. This statement was extended later by Kwon Nguyen with some extra assumption close to the boundary, and more in more general form by Sharabati. So if phi is C11, then those solutions are not only continuous, but further continuous. But so far, in those proofs, except for this item with the special case of Błotsky conjecture, the methods followed either the real case or the Monge-Ampère case. And things changed here when we considered the Hessian equation on compact Keller manifolds. So this is the statement now. Now, of course, it is different now because all M subharmonic functions on compact manifold would be constant. So we have to add this omega here. This omega is the Keller form on X. F is a given function, and we look for solutions now, not M subharmonic, but M omega subharmonic functions, which by definition satisfy those inequalities. And we want to find U for given F. So if F is positive and smooth, then this would give a generalization of Calabi-Yau from the Monge-Ampère case. And in fact, this was the first thing people tried. So just to extend the Yau's proof, and it worked up to a point. It worked under this extra assumption of non-negative bisectional curvature. It was done probably independently by Herbilou and Tokarev. But what was missing for the general case were C2 estimates. There were even some false proof published for the general case. And then the first good idea was by Hu, Ma, and Wu, who used the method of Chow and Wang, who dealt with real Hessian equations on the Riemannian manifolds. And this was done in early 2000s. So this method reduces C2 estimate to C1 estimate. And they prove the following. So if U is sufficiently smooth, then for some independent constant, the C2 norm is bounded by C1 norm plus this constant. And they suggested that one can use the so-called blow-up analysis, which transforms this equation in some coordinate patch into a homogeneous M-Hessian equation. Homogeneous meaning that the right-hand side is 0. I just mentioned that the blow-up analysis has been applied before by Xchen in this context of complex geometry. And now we come to this article which got the prize. So we completed this. So we proved the C1 estimates by using this blow-up analysis and showing the Liouville type theorem, which says that any bounded maximal M subharmonic function with bounded gradient in Cn is constant. An open question, which is still open, is if we need this assumption here. This is not what you have in the classical Liouville theorem. But some people tried and failed so far. So as I said, after having this, one can complete Calabi-Yau theorem for complex Hessian equations and show the existence of solutions for any smooth positive f, of course, with this normalizing condition on the integral. And well, almost immediately, we could also prove the existence of weak solutions if the right-hand side is in LP and is not necessarily strictly positive. P again has to be bigger than n over m. In general case, in the Monge-Ampère case, we have also Helder continuity for this LP right-hand sides. Here, in general, we do not know. Again, if you have this non-negative holomorphic bisectional curvature, then you can follow the method for the Monge-Ampère equation and get Helder continuity. In general, it's open. There is a problem of regularization. I think it was mentioned today in the first talk that sometimes you have to having weak solution, meaning non-smooth, you approximate it by a sequence of smooth solutions. And the methods which work for Monge-Ampère do not necessarily work here. So this is still open. And well, at the end of the talk, I will mention several results which use this Humau estimate and our Liouville type argument for different equations in some different spaces of functions. Recently, Guofeng and Tong applied different methods to get L infinity estimates in this setting. So in particular, you could prove this part using this different method. Okay, so now I'm going to sketch the proof of this Liouville type theorem. As I said, since it is also used in some other contexts, I tried to extract the properties of the M subharmonic functions which I used here for this proof. And if you have it for some other family of functions, then possibly you can also prove this Liouville type theorem. I'm cheating a bit here, so I will explain more. So by F, we denote the space of M subharmonic functions, which are Lipschitz continuous, which are maximal, which have values between 0 and 1. Of course, these values 0 and 1 are not important. You need to have lower and upper bound. That's it. So then you take the regularization by taking mean values over balls of radius r and center z. Here, this is not quite true. This is not in F, but in F, when you remove this maximality, it is not maximal. So I should write except for this property. Another thing which is used essentially in the proof is that if u is independent of one variable, well, it is constant in one direction, then this function also belongs to F, but of course now in lower dimensional space. Then if we take u in F and G a map from Cn to Cn, which is either complex rotation or translation or a superposition of those. So in particular, it is holomorphic geometry, then this composition is also in F. And then we need the comparison principle. I will explain more when we come to the comparison principle in the proof. It's at the very end of the proof. And now we have such a strange technical property, which we use because we have to consider two cases. Either this property holds for our in our context or not. This will be two parts of the proof. So what it says is that there exists a positive number, maps, which are those composition of rotations and translations, and a sequence diverging to infinity, so that if we take this kind of regularization for u squared, composed with gamma gk, again here, but now for u, and now this guy is fixed. This is for every rk from the sequence, and just this value. Then it should be bigger or equal this. And part B, that if we take these bigger and bigger balls extending to infinity, then in the limit, this kind of energy integral is 0. Now this magical constant here, it depends on the values on those values, 0 and 1. If we normalized u in a different way, then we would need a different constant here. That's it. Yeah. Or composition. Yeah, we will see why we need it. Well, maybe I can explain. Here we take the derivative with respect to one variable. So what we need is we need this in all directions for u, which means that if we rotate, then again we will have this. That's the point. So we use the induction, and first we know that for n equal 1, the result is no. For m equal n also, because then we deal with groups of harmonic functions, and we have Liouville theorem. Again, without lots of generality, we can assume that the supremum is 1 and infimum is 0. And C not just denotes the bound on the gradient, which we assumed. And as I said, we consider separately two cases when P, this property holds, and when it doesn't. So first, suppose the property holds. Then by Arcelor-Ascoli, you can pass to a subsequence which converges to some function v. it's easy to check that this limit function would be also M subharmonic and maximal. And then we use the part B of the property. I will go back and gradient bound to check that V is independent of the last of Zn. And therefore, by induction hypothesis, it is constant. I will explain on the board, maybe just making a picture. So here we fix Z prime, first n minus 1 variable. So this is the board when we fix, and so this is Zn plane. So suppose at 2 points we have different values of this. By this gradient bound, gradient bound, you can find disks around those points with the radii, well, the same radius, say r, which depends on this gradient bound. So that again, the infimum here is bigger than the supremum here, plus some constant, say C hat. Then we join centers by interval, but also other points from those guys. And then again, the value of V here will be bigger than the value of V here plus this constant. Which means that if we integrate along such an interval, with respect to this, this is this W direction, then we get some lower bound. Right? And then we integrate over, say, those intervals. And then we get a lower bound for in some set, E. And then by Cauchy-Schwarz, we also get the lower bound for this guy. And this is what we have in this property. This is in the property B. So we use the property B, but then we get a contradiction with property A, with part A of property P, because in particular, you remember we had this 4 over 3, and we have the bounds for U between 0 and 1. So in particular, we get this inequality for V and therefore for UK for sufficiently big K. Right? Okay, so this is the part when we assume that P is true. So now we assume that P is not true. There is a theorem in classical potential theory which uses Cartan's lemma. Oh, there is a nasty typo here. This should be 1, not 0. Here we need 1. Yeah, so using this Cartan's lemma and more general theorem of Hyman-Kennedy, we get that those limits are equal 1 for this function and for this function, using the same theorem. So, having this, first we use the translation. Remember, we assume that infimum of U is 0. So we can find a point where this is true. And then we move the origin to this point by translation. And then we use this fact with 1, as I said, to choose rho sufficiently big and R sufficiently big. Our sequence Rj will be, they all will be bigger than R. are. So having those, we obtain that the set U is non-empty because it contains 0. And the set is here. This is a setup for using the comparison principle. So as I said, property P is not true, but well, maybe I should come back to property P. This is property. So we look at the part A. We have this inequality, but now by this construction, property A holds. So it means that property B cannot hold. Therefore, after rotation, any rotation of coordinates, we have this. Any rotation because we can use this gamma, GK maps. And then it's easy to verify that having this, as I said, for any direction, we can change this direction. This form is positive, meaning that it is bigger or equal to some positive constant times beta. Then because of this identity, this is positive, our U is positive, so this thing is positive. So having the bound for this gives us the bound for the lower bound for this. And finally, we get this inequality for some positive constant C2. And now, as I said, it is a setup for using the comparison principle, but the next thing we have to check is that our set on which we use the comparison principle is bounded. A priori, it is not bounded. So we twist it by this function for a very small epsilon. So that it is a negative function. We lose some positivity in the forms. But if we take epsilon small enough, then this function is M subharmonic, which is the same as this inequality. And now this set is bounded because this guy goes to minus infinity at infinity. And now we use the comparison principle, which is similar to what we usually do when dealing with the Monge-Ampère equation. And so we have U is here on the left-hand side, and this function we have on the right-hand side. And this is just the comparison principle. And here we use the estimate from the previous slide, this one, the star. So what happens? UG is an open, non-empty open set. We started with something which is maximal, so this is 0. And we obtain that also when we change the power here to m-1, we get 0. But then we can repeat the procedure. So putting m-1 here, then we get the same thing for m-2 here. And we can continue this way, and we end up with something like this. That the Lebesgue measure of the set UG is 0, but it is an open set, so it cannot be true. We get a contradiction. So this gives the proof of the Liouville type theorem. Now I will recall a bit what is this blowing up analysis, which is used to finish the proof of Calabi-Yau. Namely, suppose we do not have C1 estimate. This means that we have a sequence of functions which are C2, such that they satisfy. Okay, so we consider the right-hand sides of the equation. We solve, and if we do not have the a priori C1 estimate, then for some solutions we will get this bigger and bigger constants. Those maxima are realized at different points. So we pick the points where they are realized. We can pass to a subsequence so that they converge to one point. So in particular, almost all of them are contained in one chart. There's a bit of mess in the notation. Here, ZJs are points. Maybe we should write like WJs, because the same notation is used just for coordinates. And now, having those solutions on the manifold, phi j's, we produce functions in one fixed coordinate chart. So they are defined in bigger and bigger balls because CJs tend to infinity. And if you put these UJs into the equation, you obtain this. Now what happens? CJ go to infinity, so it means that this forms tends to 0 when J goes to infinity. Here, FJs are bounded, but those guys again go to 0. Right? So in the limit, we will obtain DDCU J to the power M wedge this equals 0. As I said, UJs are defined in larger and larger balls. So in the limit, the limit is defined on Cn, and solve the homogeneous Hessian equation as I explained a second ago. Using Humau estimate, we have the bound for the second derivatives because we have the bound for the gradient. Maybe I go back. This is because if we take the gradient of this at the point Zj, it is equal 1. The norm of this gradient is equal 1. So we have the bound for C1 norm, which gives us the bound by Huma and Wu, bound for C2 norm. Having the bound for C2 norm, we can use Arcelor-Ascoli and diagonal procedure to extract sequence which converges in C1 alpha for any alpha between 0 and 1. So we take the limit, and we denote this limit function by U. It satisfies the homogeneous Hessian equation, but on the other hand, by construction, the gradient at 0, well, 0 is the limit of those ZJs. The gradient at 0 is 1. And we get a contradiction with this Liouville theorem proven a few slides ago. Okay, that's the end of the proof of Calabi-Yau for compact Keller manifolds. So now about works which appeared later and which used this method of first Huma-Wu and our Liouville type theorem. Gabor-Szekely generalized this gradient estimate to wider class of differential equations, and background Hermitian metric, not necessarily Keller. So this generalization goes like this. We consider open cone symmetric gamma, which contains gamma n, so it contains all positive eigenvalues, and is contained in gamma 1. We now consider Hermitian manifold with with this fundamental form omega, and some other real 1-1 form alpha. This notation alpha u stands for alpha plus ddcu. Now, instead of this lambdas considered before, we consider eigenvalues of the endomorphism of tangent bundle defined by alpha u relative to omega, which will be explicitly written on the next slide. And also, the differential operator is much more general. So we assume that f, this differential operator, is symmetric in lambda. So if we permute lambda j's, then we get the same thing. It should be increasing in each lambda j. Here, if on the boundary of the cone, the operator f is, well, we require that this operator on the boundary is smaller than the infimum of g. G is the right-hand side of the equation on x. And we have this condition, so we take any number delta, sigma, smaller than supremum of f, and then we take the limit of f, so we go in this direction of lambda to infinity, then you should get something bigger than delta. It gives us certain compactness. Okay, so those are assumptions on the operator. And the family F, which I described in the proof of the Liouville type theorem, is now replaced by subsolutions for this more general equation. And the subsolutions are defined here. So V is a subsolution if this set of lambdas satisfying this and this condition, gamma n, denote this cone of lambdas with all positive coordinates. This should be true for any matrix of this endomorphism which I mentioned. The matrix is given by this trace. And Gabor proved that it satisfies, up to some modifications, the properties needed for the proof of the Liouville type theorem, and he got the same proof here. Of course, he had to also work with modification of Humau estimate, and finally he got he obtained solutions of, well, both just Hessian equations, but also Hessian quotient equations with constants here. This is the Hessian quotient equation in this Hermitian setting, but just for Hessian equations, the proof were given by Wei Sun and Dekai Zhang before Gabor's work. So Gabor got in particular this, but also more general solutions of Hessian quotient equations. Another use of this method was by Tosati and Weinkopf. So they dealt with so-called form-type Monge-Ampère equation. which is described here. Now we are back on the Keller manifold. Omega is another Hermitian form. F is a given function, smooth and positive. And one would like to solve this kind of equation. It needs some explanation because we have n-1 form here. What does it mean that we have the determinant? So this by duality by Hodge-Star, you have dual 1-1 form, which has coefficients. And then you take the determinant of those coefficients up to constants involving also signatures. Because you have two coefficients and depends which one is first. But anyway, there is a definition of such a thing. And you want to solve, so you want to find a constant C, which is not a priori known, and the function U, which satisfies this inequality, but also this equation. And they succeeded this, and they used the Slawomir type theorem now for so-called n-1 pluri-subharmonic functions, which by definition satisfy that this is non-negative. They were also studied before by some other people, Verbitsky, Harvey, Lawson, maybe some other. I'm not completely sure. But there was a previous work considering these form type equations by Fu, Wang, and Wu. And they obtained special cases where there are some curvature assumptions satisfied. But they also noted that non-Keller solutions of those equations, solving those form type equations give you also non-Keller solutions to one of the equations in the Schrödinger system on Calabi-Yau Keller manifolds. And this equation is given here. So omega is, I think it also appeared on the first talk today, the non-vanishing holomorphic n form on X. And you want to solve this. So solving this form type, you get this. The same equations also give you Calabi-Yau type theorem for balanced metrics, for Goduchon metrics, and for strongly Goduchon metrics. Balance are defined here. Goduchon will be defined on the next slide. So again, you take another. You take omega not satisfying, for instance, balance condition, and then you solve. You want to find U solving this. No, if you define omega U in this way, then it solves this equation. That's the point. So this Tosati-Weinkow work was continued now with also with Gabor Szekely-Hidi, and they solved Goduchon conjecture. So so this is the definition of the Goduchon metric, which is far more general than Keller case, because on a compact manifold you not necessarily have a Keller metric, but on any complex manifold you have Goduchon metric. And there is an analog of Calabi conjecture for Goduchon metrics, which says that given Chern-Ricci form, which was also defined today, I think. This is Chern-Ricci form, which in the Keller case is Ricci, but in non-Keller case, it is different than Ricci. So now having this Chern-Ricci, you want to find the Goduchon metric which has this Chern-Ricci form. And then it appears that you have to deal with such an equation. This is the equation, and this is the definition of alpha to the power n minus 1. And again, using the same strategy, Humau, again, you have to work with a new type of estimate, and with the type estimates, you get also existence of those Godushon metrics. I should hurry up. So this is the next last slide. Some time ago, before our result, Fu and Yao considered also some so-called Monge-Ampère type equations, but only in dimension 2, because with some ansatz, you could reduce the Hall-Strominger system to this Monge-Ampère type equation. Here you see what this gives you. If you solve this system, then the solutions give a toric vibration over K-free surface. But in higher dimensions, instead of Monge-Ampère type equation, you obtain some kind of Hessian type equation with some specific chi and psi here. This is a more general form, which was studied by Fong, Picard, and Zhang in several papers. So for some data which corresponds to this Hall-Strominger system, they could solve the problem again using the method, but now just for two subharmonic functions. So this is the case we dealt with, exactly with which we dealt. Okay, thank you.
All right, so any questions or comments? So my question is on page 12, you mentioned on some like Hölder regularity of the solution by putting holomorphic bisectional curvature assumption.
Well,
I think on page 12, if I remember correctly.
okay.
Yeah, so you mean there by chance there is non-negative holomorphic bisectional curvature? Is this coming from some maximal principal argument? Why we need the
What I
curvature
understand
assumption?
is because in general the problem is to produce these regularizations.
Yeah.
So having a weak solution, you want to approximate it by smooth solutions, and with this assumption, the method we used for instance, for Monge-Ampère equation works. So you can kind of use a similar approximation, and then the point is that these smooth solutions you produce, smooth functions you produce are M subharmonic. In general, we don't. I mean, they are probably not M subharmonic.
All right. More questions?
Singular, can your estimates work?
No idea. I don't think Humau. I mean, first you need Humau, and in presence of singularities, it's because the point is that you take you start with the point where Hessian is maximal, and the none of the Hessian is maximal, and because, well, if you have singularities, then you kind of move from compact to non-compact situation.
Yeah.
And then you don't even find this point.
Okay, thanks.
More questions? Okay, so if there is no further question, let's thank Professor Kolodziej again.